Good evening, everybody. A good start to this problem would be just to factor this coefficient of x squared. Um, see if it does factor, and then see if we get lucky, okay? Now, uh, that's perhaps not the best way to start the video, but if we notice that this possesses the very same linear factor as the coefficient of x cubed, that's going to prove to be quite useful here. So let's just write this down. And it doesn't take too long to perform this multiplication. There is a divisibility test for 154 and it for 11, okay? And that means you go 4 minus 5 plus 1, which is equal to 0. That's the alternating divisibility test for 11. So again, 4 minus 5 is negative 1 plus 1 is 0. That implies this is divisible by 11. Now, you don't really need to do that if you just observe 11 times 14 is 154. Okay, for larger numbers, perhaps that divisibility test is okay. So what we have right here is these factors. K plus 7, since minus 7 is a 0. K plus 11, since minus 11 is a 0. And then, what do we got? K plus 2. Now again, this would be useful to consider this factorization here. Independent of the instructions almost. Okay, now I know that sounds flaky, but notice we do have k plus 11 right here as a factor of this cubic, and k plus 1 is the coefficient of the leading term. All right, now, one thing to do to get this thing going in terms of trying to eliminate some possibilities, notice that if k is equal to negative 11, both of these terms vanish, and you just have bx plus c is equal to 0, and we get x is equal to minus c over b. So of course b can't be equal to 0. In this very special case here, we're just talking about if k were equal to 11. Here's what would sort of boring here. B can't equal to 0, and c would have to equal to 0 for this to work out, right? Because it's the only 0, so it must be 0 if the roots are going to sum to 0, right? So not interesting at all. But at least we got that out of the way. And so what we can do now is divide through by k plus 11. And we'll go ahead and make, of course, we're making the assumption that k is not equal to negative 11 because we've already established what's happening here. If k is equal to negative 11, well, that would force c to equal to 0. So that would be such a k. But it's kind of trivial with respect to the rest of the problem. Now what I did right here is divide through by k plus 11, and you can see that cancel this factor right here. And then if you divide through by k plus 11, you're only left with the linear factors k plus 7 times k plus 2. And it's inconsequential what the values of b and c are here at this point. Okay, it's very interesting. All we have to do is find the k's that force the coefficient of x squared to be equal to 0. And y'all, this is the justification for that. If omega, rho, and delta are the roots, then we get this expansion, by the factor theorem, we get this expansion in terms of the roots. And as you've seen, many of you have seen, you probably don't need to see this, the minus sum of the roots present as the coefficient of x squared. Okay, that is minus delta, minus the quantity delta plus rho plus omega ends up being the coefficient of x squared. Okay, and that's all that's really important, because that means we have to set what presents, if you want to call it that, as the coefficient of x squared. Well, we see that k plus 7, it's already not factored for us, which is useful. Okay, so we have k plus 7 times k plus 2. And those of you that have Vieta's memorized, or you just understand the principles of how the roots present as coefficients in various forms, they're called elementary symmetric polynomials, by the way. But you get this is equal to 0, and the 0 that you see right here would be, what happened? We're saying the roots have to sum to 0, right? The roots, find all values of k such that the roots have to sum to 0. Well, here's your roots, and they have to sum to 0, right? But this is the special case situation going on here for this particular one, or it's just the nature of this particular problem. But anyway, we see quickly that we find k is equal to -7 or negative 2. Okay. Now, hopefully I presented this in a fashion that makes a little bit of sense. Maybe you don't think so, but you see you do have to resolve what's going on when k is equal to negative 11. All right, that's pretty clear. But like I say, if k is equal to negative 11, this part is 0, this part is 0, you have bx plus c is equal to 0, and you get this condition right here, x, it's just a linear case, x is equal to minus c over b, and of course b can't be 0, and c has to be equal to 0. It's a force fit, okay? So when k is equal to negative 11, you get and c is equal to 0, you get the sum of the roots are 0 in a trivial fashion. Now this part right here is a little more fun, because now that we can divide, now that we resolve the case for k is equal to negative 11, we can divide through by k plus 11 because we're not dividing by 0, right? So no problem there, and everything works out nicely. And the part that's sort of interesting about this, I guess, is that b and c are free-ranging variables. It makes no difference. Make up your own fun problem here, and you'll see that this works, folks. You could use this to generate an infinite number of problems. Not that that's particularly interesting, but b and c can be any real numbers you want outside of this special case right here. It's a force fit right here for this special case when k is equal to negative 11. But as long as k is not equal to negative 11, no matter what constants you choose, b or c, the answer to the question is negative 7 and negative 2. Alrighty, folks. And by the way, y'all, this is called Vietta's formula. This is a justification for Vietta's formula for the cubic case. All right, that's all. Thanks for viewing.